we know that a single point charge in space will repel any other point charge placed near it. Meaning if I bring another point charge in space right here, it will experience a force of repulsion in this direction. If I take that charge and move it over here, it will experience a force, of course, in this direction. But it'll be a bigger force because it's closer to the central particle. If I take this and say move it over, I don't know, how about here? It will experience a force like this, but it'll be even smaller because it's further away still. If we keep moving this charged particle around, we can begin to build a pattern for the nature of forces on charges in the vicinity of this central charge, which is a fancy way of saying that we could build a model or a map of the force lines around this particle. This process is the basic idea for defining what the electric field might look like around a particle. And it's not particularly complicated. I think you guys can probably imagine what this would look like. I can kind of draw it here. And around a central charge, there is a pattern to the nature of the field. Something like that. The electric field lines have specific properties, and you need to know these properties because you might be required to do field mapping. So let's talk about some of the properties. First, the field lines point in the direction a positive charge would be pushed. That's incredibly important because positive charges experience a force in the direction of these arrows. Negative charges experience a force in the opposite direction of these arrows. These arrows don't represent force, they represent the electric field. The concentration of these lines suggests how powerful the electric field is. So the more concentrated the lines, the stronger the field. We know that as you get farther away from a charged particle, its ability to influence you is reduced. Thus, Coulomb's law, which clearly states that as you get further away, you experience less and less force. However, and this is the most important thing I'm going to say today, the electric field is a construct. The electric field is a construct. It's something we created to help us understand the space around charged particles. I'm trying to be very clear about this because I need you to learn this definition. And it's complicated. The electric field is not something about the charge. It's something about the space. When I'm done talking about the electric field, I don't need to know what was there before. All I need to know is what the field is. So when we calculate the field, often we are calculating something that's going to have information about space in it. Meaning I generally want a function of the electric field in terms of location. What is the electric field here compared to the electric field someplace else? So we will be calculating the electric field generally in terms of position. What is the electric field this far away from this charged object? Sometimes it'll be very complicated and we'll build a two-dimensional map. Sometimes it will be very, very simple and will be very one-dimensional. But almost always we are attempting to find the electric field at some specific point in place due to the nature of charges in that vicinity. Now, to understand why the electric field has importance, I want to go back to something that we already know about, but was not taught like this in school last year. Let me draw myself a quick picture. A house? Is that a house? Okay. All right. A hillside next to the house. Everything okay so far? All right. So, if I walk up the hillside and I'm standing here, and I have something I can drop, and I decide to drop a ball towards the ground, is there a different force acting on that ball if I am up here? Like, do we know the difference in the gravitational field between these two places? What would be the acceleration of gravity at this point, at the lower point? Yeah, I'm not trying to ask hard questions. 9.8 meters per second squared. And what's the acceleration of gravity at the higher point? Yeah, we say this because the gravitational field near the surface of the Earth is relatively the same everywhere. In fact, we defined gravitational field by taking the force of gravity on an object and dividing away the object's mass. This leaves us something that tells us about an object without ever having you need to ask, how big is the object? Which none of you did. None of you had to know how big the rock was that I was holding in order to answer the question about what the acceleration is. Because we know, we were told, that all objects experience the same acceleration no matter how far from the Earth they are, as long as they're close to the surface of the Earth. And it doesn't matter how big it is, if I have a little rock and a big rock, they'll still experience the same acceleration of gravity. What was not told to you is that the acceleration of gravity was convenient as a means of teaching you things about motion, but should have been written not in meters per second squared, but in terms of newtons per kilogram, since we were actually talking about the gravitational field, not the acceleration due to gravity. The reason I say that is the goal here was to give you something where you could figure out the force on any object once you knew the gravitational field at that point. Isn't that how we calculated the weight of everything last year? We took the acceleration of gravity and multiplied by m every single time. That's because what we really had in this lowercase g was the gravitational field. In terms of newtons per Coulomb. That's the goal of the electric field, to provide us a value, something that can tell us about space, so that we could put any charge at that point and know how much force that charge would experience. That's what the electric field is about. Is if I know the electric field at this point in space, no matter what charge I place there, Q, Q2, Q3, no matter which one of these charges I place there, because I know the electric field, I could tell you the force on any of those charges. So we define the electric field by the size of the force a particle would experience there. It's a weird definition and will take some getting used to. But again, the electric field is defined by the size of the force a particle would experience at that location. This is the definition of the electric field. It's a little hard to wrap your mind around in the beginning. But eventually, we'll find ways of calculating the electric field without having to deal with force. Right now, we can't. So, some important details. Electric field is measured then in newtons per Coulomb. That is the prevailing unit of the electric field. We will learn another unit later, but right now, this is the one you need to know, newtons per Coulomb. This expression can be written two different ways. This is often the other way it is written, or Q times E, it doesn't matter. I don't know which one's on your equation sheet. Be aware, all of these are vectors, but the size of charge is a scalar. But again, the important detail, the one that you need to be really driven home, is that if I tell you the electric field at that point, I'm giving you something that is about that place in space. It does not tell you what will happen to a charge there, because we would need to know how much charge we're placing there. It would, however, tell us, if I knew what the electric field was, I could figure out what would happen to a point when placed there. Let me say that again, because I kind of stumbled over it. Imagine I told you that this point in space had an electric field of 2,500 newtons per Coulomb. Electric fields tend to be big numbers. If I say that that's the electric field right here, and that it's in this direction, then you would know the force experienced by anything placed there. So if I tell you I'm going to place a 2 microcoulomb charge there, then you could say, okay, the force on that particle would be equivalent to this product. If you knew the force, you could probably use some Newton's laws to figure out what would happen to the particle. You would need its inertia, sure. But by telling you the electric field, I'm giving you a method of figuring out how particles will react when placed at these kinds of placed in these regions in space. What I'm going to need us to be able to do is I need us to be able to do two different things. First, you need to tell me what happens to a particle placed in a location of space that has an electric field. That part seems obvious. You're just going to use. But I also need you to tell me the size of the electric field. And the only way to do that right now is using Coulomb's law and a test charge. This is the process that we're going to learn. How to find the electric field by using Coulomb's law and a test charge. This isn't particularly hard, but it requires us to do a two-step process to get to the electric field. The best example is just to say this. Imagine I have a central charge. We'll say it's, Q. And I want to know the electric field right here. To figure out the electric field at that location, I would have to do three things. Step one, I would have to create a test charge. Test charge are small and they're positive. Step two, calculate Coulomb's law. And step three, divide out the test charge. It's a bizarre set of steps, and we'll practice this tomorrow.